Hello everyone, my name is Charlotte Deng from Institute of Geodesy, University of Stuttgart. Today my topic is superposition error elimination effect of a spherical shear and a spherical runner bond discretized into tesseroids in gravity field modeling. This presentation has 5 parts: introduction, theory, numerical experiments, conclusions, and outlook. In general, a spherical shear is often used as a benchmarking tool in gravity and magnetic field modeling. This is the finger of a spherical shear on the right side. This is a tesseroid in spherical coordinates on the right side. A spherical shear can serve as the benchmark for different types of mass bodies. For example, the tesseroid, triangular, and hexahedral integrations. The reason is that gravitational or magnetic effects of a spherical shear have analytical solutions no matter where the computation points are. Meanwhile, a spherical zonal bond has often been used as a geometrical element to test and validate different numerical methods of the tesseroid in gravity field modeling. This is the finger of a spherical zonal bond on the left side. This is a spherical zonal bond equally divided by the tesseroids along the longitudinal direction on the right side. Similarly, the reason for spherical zonal bond to be the benchmark is that gravitational effects of a spherical zonal bond have analytical solutions when the computation point is located on the polar axis or z-axis. The current issue is that most of the above-mentioned studies focus on global errors of a whole spherical shear or a whole spherical runner bond rather than local errors of the individual tesseroid. The numerical results or conclusions from those global error assessments cannot be applied for local practical calculations. The superposition error elimination effect means the possibility that the symmetric of the global spherical shear with the discretized tesseroids might cancel out some errors from individual tesseroids. This SEEE is only a hypothesis that has not yet been validated by numerical experiments. Concerning the spherical shear and the spherical zonal bond discretized into tesseroids, it's necessary to analyze the SEEE by comparing the global errors of a spherical shear and the spherical zonal bond with the local errors of individual tesseroids. Consequently, it's important to examine the variation of local errors of the individual tesseroids in details. The challenge of evaluating the local errors of an individual tesseroid is to derive analytical expressions for the gravitational effects of a tesseroid. This is difficult since the concept of the tesseroid was proposed in Anderson 1976. The preliminary reason is that in the general formulas of the gravitational effect of a tesseroid, the double integrals of the longitude and latitude or latitude coordinates are considered incapable of analytical integrations in previous studies. However, some research progress has brought it at a turning point to this challenge and provided the research idea for the solution of this difficult problem. The key idea is the special condition of the computation point located on the polar axis. In other words, when the computation point is located on the polar axis, the analytical solutions for gravitational effect of a tesseroid can be obtained. Let's go to the theory part. This is the general formula of the gravitational potential of a tesseroid. When the computation point is located on the positive side of the polar axis, we derive the analytical formula of the GP of a tesseroid. The first order derivatives of the GP are the components of the gravitational vector, short for GV. Under the same condition, the analytical formula of the radial gravitational vector VR of tesseroids from the general formula is presented. The detailed derivation of three components of the GV can be referred to Appendix B of Dunn and Snew 2023. The second-order derivatives of the GP are the components of the gravitational gradient tensor, short for GGT. Regarding the three components of the GGT, VZZ, VXX, and VYY of a tesseroid, their analytical expressions are derived from those general expressions when the computation point is located on the polar axis. We use Laplace equation to validate the correctness of those derived expressions for the GGT of a tesseroid. In other words, the sum of those three analytical expressions is equal to 0. The detailed derivation of 6 components of the GGT can be referred to Appendix C of Dunn and Snew 2023. The third-order derivatives of the GP are the components of the gravitational curvature, short for GC. Herein, we derived the analytical expressions for 3 GC components, VZZ, Z, VXXZ, and VYYZ of a tesseroid when the computation point is located on the polar axis. Similarly, those 3 expressions satisfy Laplace equation. In other words, the sum of those 3 expressions is equal to 0. The detailed derivation of 10 components of the GC can be referred to Appendix D of Dunn and Snew 2023. Generally, a tesseroid can be treated as a sector of a spherical zonal bomb. In other words, when the longitude of the integration point integrated from 0 to 2 pi for a tesseroid, a spherical zonal bomb is obtained, letting lambda 1 equal to 0 and lambda 2 equal to 2 pi in the derived expressions for tesseroid. The analytical solutions for the gravitational effect of a spherical zonal bomb are obtained. Those GGT and GC components of a spherical zonal bomb satisfy Laplace equation. The other components of the GV, GGT, and GC of a spherical zonal bomb are equal to 0. In general, a spherical shear can be discretized into tesseroid with respect to the longitude, latitude, and radial directions. When the longitude of the integration point integrates from 0 to pi, and its colatitude integrates from 0 to pi for tesseroid, a spherical shear is obtained, letting λ1 equal to 0, λ2 equal to 2 pi, θ1 equal to 0, and θ2 equal to pi. In a derived expression for tesseroid, the analytical solutions for the gravitational effects of a spherical shear are obtained. It's easy to find that these components of the GGT and GC components of a spherical shear satisfy Laplace equation. The other components of the GGT, GV, and GC of a spherical shear are equal to 0. In a numerical experiment, we use 3D GRQ to obtain the numerical values of gravitational effects of the tesseroid. Numerical values of the parameters are presented in this table. The first experiment is the influence of GRQ orders on gravitational effects of the tesseroid, spherical round bond, and spherical shear. The relative errors of the gravitational effects of A, a tesseroid, B, a spherical zonal bond, and C, a spherical shear are presented. The x-axis means the GRQ orders, and the y-axis means the relative errors in log10 scale. In general, regarding the gravitational effect of the single tesseroid and spherical zonal bond, as the 3D GRQ orders increase, the relative errors decrease and remain at a certain level. The relative errors of the gravitational effect of the spherical shear declined with the increased 3D GRQ orders. The second experiment is the influence of grid size on gravitational effect of the tesseroid, spherical round bond, and spherical shear. The relative errors of the gravitational effect of A, a tesseroid, B, a spherical zonal bond, and C, a spherical shear are presented. The x-axis means the grid size, and the y-axis means the relative errors in log10 scale. Specifically, with the increased grid size of the single tesseroid and a spherical round bond, the relative errors decrease first and then increase. For the spherical shear, the relative errors of all gravitational components decreased with the increased grid size. The third experiment is comparing gravitational effect of every individual tesseroid forming the spherical zonal bond and spherical shear. Here is the comparison for the spherical round bond. Here is for the comparison of the spherical shear. Numerical results demonstrate the existence of the SEEE both for spherical zonal bond and spherical shear. For the conclusions, we derived analytical formulas of the gravitational effect of a tesseroid, where the computation point is located on the polar axis. Based on those newly derived expressions, the analytical expressions for the gravitational effect of a spherical round bond and the spherical shear are obtained. In summary, numerical experiment demonstrate the existence of the SEEE, both for spherical zonal bond and spherical shear. It shows that the analytical solutions for tesseroids can contribute to further investigation of this SEEE. For the outlook, on the basis of those newly analytical formulas of a tesseroid, a single tesseroid benchmark can be proposed in comparison to the spherical shear and the spherical zonal bond benchmarks in gravity field modeling. Detailed numerical analysis will be performed on the investigation the SEE of a spherical shear and a spherical zonal bond discretized into tesseroids. If you want to know more details about this research, please refer to this paper. That's all. Thank you for your attention.